So thank you very much, James. Okay, so my talk is going to be about not necessarily what machine learning can do for improving data assimilation method or used within the assimilation method. It's going to be more used like a tool to actually learn new data assimilation schemes, or maybe look back at some of the methods that we are using in data assimilation, and maybe we didn't fully grasp some of the key concepts behind them. So this is more like a discovery tool that I'm going to use AI for today. Okay, so the framework, I'm going to use very simple notations, and those are with the equation one. This is the traditional data assimilation setup that I'm going to use. One thing I'd like to focus on is the fact that I'm going to use a forecast model, which is not depending on time. It's an autonomous model for the sake of simplicity, and also it is going to be a traditional observation equations with this HK observation operator and additive Gaussian noise. So very simple, traditional data assimilation framework. And also, I'd like to emphasize the fact that I'm going to be playing with those concepts within a sequential data assimilation framework typical of geosciences and methodology oceanography. So this is something we have to keep in mind, and focusing on chaotic model. And so the first thing that I'd like to remind us is the fact that the key differences and key differences that have an impact on accuracy for all the main traditional data assimilation method. So I'd like to recall that actually, first of all, the variational methods can handle nonlinearity operators, that they can usually handle asynchronous observations, but in their basic form, they cannot handle the errors of the day, so the dynamical estimation of the errors within the scheme. However, the ensemble filtering method, so typically the ensemble Kalman filters, they can only handle weak nonlinearities of the operators. They cannot, in their basic form, handle asynchronous observations. But, and this is their main strength, they can handle the errors of the day. So this dynamical estimation of the errors, especially through the ensembles, even though it requires some regularizations, as we know. And so the typical test, numerical experiments that you can do on low order models or typical toy models, such as the Lorentz 96 model that I'm going to use later on in the next slides. You can actually see that when you, and looking at the accuracy, so typically the root mean square error in such twin experiment, for small to moderate window, data assimilation window size for the 4D var, the NKF really has the edge on 4D var very clearly, because it can handle these errors of the day through the ensemble. So actually, so the NKF actually beats easily the 4D var for small to moderate time windows. And 4D var needs, in this context, 4D var needs a very long, actually 4D var needs a very long time data assimilation window to actually beat the NKF. Okay, but now back to the topic. So here I will assume, so the goal here is really to focus on what AI can teach us about data assimilation. And the specific focus will be on learning the analysis step of a sequential data assimilation scheme. So the first hypothesis that I'm going to make is that I'm going to assume that I know the forecast model, which is something that we can play with with machine learning. And we could actually easily lift this hypothesis and actually learn the model altogether. But I really want to focus on the analysis part here and just assume that I'm going to learn the analysis and not the model. So the model is supposed to be known, the forecast model. And the analysis step is just summarized with this, encoded in this formula here. And this is an incremental update, like we usually do in data assimilation, where the analysis ensemble is actually given by the forecast ensemble plus the correction of the analysis that I made dependent on the forecast ensemble, as well as the innovation, but which is projected back to the state space. Okay, so that's a trick that is super useful in the following, but it is not really key to what I'm going to say later on, although it's very, very convenient. But the key point here is that there is this both dependence, so dependence on the forecast ensemble and the innovation projected back, so lifted to the state space. Okay, and for the forecasting step, I mean, this is just like in the ENKF forecast in ENKF for particle filters. This is just forecasting the analysis ensemble to the next forecast ensemble at times tk plus 1. Okay, and I'm going to use, so the A theta is the operator that I'm going to learn. So typically a neural network, and theta is the set of weight and biases of this neural network. And I'm also going to call down, so for data assimilation network, the whole scheme that is actually using this A theta operator. And so for this A theta, you can actually choose any kind of neural network, but I'm going to focus, and this has some importance, where I'm going to focus on the convolutional neural network here. And because, of course, the Lawrence 96 model that I'm going to use, that I'm going to play with, it's a one-dimensional model, so that actually it's going to be useful to use this convolutional neural network structure. But it's a basic one. Okay, so in the literature so far about learning this analysis step, there are not so much papers, but there are a few important ones. And there's been a few very early papers on trying to learn this analysis step through the output of data assimilation schemes. I mean, a large database built from a data assimilation outputs. So this was one of the first things that people did. Also, people have been playing, and this has been reinforced recently, using auto-differentiable data assimilation method, like typically the ENKF, and trying to tune some of the parameters of the ENKF through the auto-differentiable structure of the ENKF. I mean, the way they encoded the ENKF. But about non-parameterized analysis of these operators, there are only a few papers that I'm aware of, like Bocquet and Boudier recently, that really try to learn this analysis operator in a non-parametric way, at least parameterized by this neural network, but it's a very general way of doing so. What I'm going to use here is, at least for the loss function, it's going to be similar to the one of Bocquet and Boudier. And the loss function that I'm going to use is just to an experiment where I have access to the truth, and I want to learn, the analysis, so this incremental analysis that I've written before, to match this truth. So it seems like a very simple loss function. Okay, just comparing the truth with the analysis. However, the difficulty actually resides in the fact that the dependence in between the cycle, because this is sequential data assimilation, and I want to carry all the information from one cycle to the next. So there is this the implicit dependence in the weight and biases of the neural network that parameterize the F theta, and this is where actually the difficulty resides. Okay, so this is where it's not so easy actually to code this kind of scheme. But so there are ways to do so, even though it's costly. But there are ways to do so. So I don't really have time to go into the details. But there are really a way to try to learn those parameters through several cycles. Although not all the cycles, it would be too costly, but through a few cycles of the sequential data assimilation scheme. And we're going to try to learn those theta parameters of the neural network through those cycles using this loss function. Okay, so the first typical thing that we would do is some kind of a hyperparameter sensitivity analysis, because of course there are many parameters in this sequential data assimilation scheme, the one that we want to learn. And so we can try the dependence in the data sets, the learning data set size, the training one. And also we'd like to look into the dependence in the number of filters that we have in the neural network to learn these theta parameters. And we've got to strike some compromise between the accuracy and the speed of learning these schemes. And so those are the typical parameters here that I've chosen. But the main starting point is the fact that we can actually, when you look at the Roman square errors, and when you know actually typically what the Lawrence 96 can give you in terms of accuracy, it's right striking that actually you can reach almost the accuracy of an ENKF you can learn actually a scheme that is as efficient as the NKF. And this is the first striking feature. But the main one actually is when you look at the dependence in terms of the size of the ensemble. So in this analysis ensemble and forecast ensemble, and this is the curve typically where you look at the mean square error as a function of the ensemble size, and you see that actually there is barely no dependence in the ensemble size. And actually, if you choose an ensemble of one only member, so you only forecast one member, it turns out that you can actually reach the accuracy of the ENKF, so with only one member. So that is really strange and really contrary to what we've learned so far in data assimilation. So that is the first thing that I'd like to emphasize. So of course it means that you don't need, because we didn't use that. So you don't use inflation or localization in this scheme. And also another remark is that it is super robust to any kind of perturbations. It does learn some kind of inflation schemes, behind the scenes. We don't know how, but it actually learns some things, and it is super robust, in addition to being very accurate. And so in the following, I'm going to assume that I've got only one member. And we made a few comparisons with typically what we would obtain with 3D bar. So with 3D bar, we would obtain a mean square error of 0.40. With an ENKF, you would obtain, depending on the ensemble size, you would obtain something like in between 0.18 and 0.19. And here, with this compromised number of filters, you actually get 0.19, and you can go below if you increase the number of filters in the neural network. But if you suppress the dependence in the forecast ensemble in F theta, it turns out that you fall back to the 4D bar performance, which means that actually the F theta, so this learned analysis actually extracts some informations from this single state, because now the ensemble is a single state. So there is something really, really nice here, is the fact that really it learns some features from the forecast states to actually give this very accurate scheme, as accurate as the NKF. And so to explore this idea and really try to understand what's actually happening behind the scene, we like to compare this F theta, or make some kind of Taylor expansion of this F theta to match our traditional way of seeing data assimilation, so typically through a Kalman gain. So we like to expand this F theta in terms of a Kalman gain and the innovation. So that's typical expansion here. And so to check this, we like also, of course, to check the bias. So any constant term that would appear in this expansion. So that's the BK. And so we can numerically test how big is this bias. And we could make this in a numerical way. We can make this expansion of F theta to try to actually guess what would be the kind of equivalent Kalman gain for this scheme. And you can make regressions actually to least square problem to actually estimate this K, and this is what we've done. We could also access the analysis error covariance matrix, because rather than expanding in terms of the innovation, we could expand in terms of these whole second variables in F theta, which I call zeta. And if you make this expansion, actually what you recover is not the Kalman gain, the equivalent Kalman gain, but some equivalent analysis error covariance matrix. So that would typically be the analysis error covariance matrix that this F theta yields or represents implicitly. And so we'd like really to have access to those objects and see what this F theta does. So checking that numerically, we see that B is actually very small, so there is almost no bias, and you can make this some kind of Taylor expansion in terms of a Kalman gain. And the second point is that we also run a concurrent ENKF, a well-tuned one, to compare actually what F theta was doing and what the ENKF was doing, and we compare the analysis error covariance matrix of the ENKF with the analysis error covariance matrix, or the equivalent one from F theta. And they're actually quite close to each other. So F theta is doing, this learn scheme with only one member is actually doing something very similar to the NKF. And you can actually check the spectrum of those analysis of covariance matrix and see, yeah, that for the main modes, the DAN scheme actually does, I mean, there it got the same modes actually as the ENGF, or very similar. But for higher index, it applies some multiplicative inflations, as you would expect for a very robust scheme. And this is exactly what's happening here. This is exactly what we see. So some multiplicative inflations for the higher index of the modes, and essentially the same as the one as the ENGF's modes for the bigger ones. Okay, so the conclusion that we got here, the first conclusion is that actually, so it does depend on innovation, but mostly it extracts some information from the forecast states. The second conclusion that we got is that it looks like it is doing something very similar to the NGF. So we have to conclude that actually Theta learns directly about the dynamical features of about these errors of the day, and from them it is able to actually build its own representation of the analysis error covariance matrix. And one explanation for being able to achieve that is the fact that there should be some multiplicative ergodic theorem that not only applies to the underlying dynamical model, so Lorentz 96 in this case, but actually to the whole data assimilation schemes. And that actually would be a way to explain why we are able to actually use only single member, single forecast state actually, and do almost as well as the NKF. And the last experiment actually is doing the same experiment, but doing Lorentz 96, but learning from different size of the Lorentz 96, so from 20 to 160. And you realize, and but keeping the same structure and numbers of filters actually in the convolutional neural network is actually the very same one neural network. But then you learn, of course, a new theta for each dimensions. And it turns out that you end up with very similar accuracy. And so actually, there is no, you don't have to make the convolutional neural network bigger actually to get this good accuracy, which seems to imply that actually the features that are extracted from the forecast state are actually local. And the last experiment that we did is that because it's a convolutional network, we actually can apply it to a different size, a different Lorentz 96 size, and I can train it. I can train them on the Lorentz 96 with a size, the typical 40 number of sites, and apply this learned theta on the bigger model, like with a size of typically 80 or 120 or whatever. And it turns out that it works. So there is this kind of transformational transfer that actually you can use a model trained on a much smaller model, and it would actually work in this context as well with the same accuracy on a higher dimensional model. So really it proves that that whatever information is extracted from the forecast state, it is actually local. And yeah, so to conclude, I mean, I try to make my point about what we actually can do with this and what we learned with this theta, the fact that actually it can work on one single member forecast state, that it has to learn to achieve the accuracy of the enquete. It has to learn some local patterns in the states. And I mean, there is a connection with mathematics and the multiplicative ergodic theorem, but I don't really have time to discuss this. But I also to stress the fact that it works with other types of low-order models, such as the Kuromoto-Shubasinski model. And it can also be trained in non-supervised, I mean, or semi-supervised settings where you don't actually have access to the truth, but only the observations. And so really that's a way to look back at what we are actually doing with the NKF and try maybe to devise new data assimilation method based on this intuition. And you can find these findings actually in this paper. Thank you very much.
Hey, great. Thank you very much, Marc. So we do have multiple questions on the Yopad. We don't have too much time, but we can have time for a few questions. First question from Philip. So the performance of the neural network is independent of the ensemble size. Does that mean that the neural network manages to distill the same information and ENKF gets from an ensemble from the historical information contained in the cycles used to train it. In essence, using a type of historical ensemble.
No, it's not. It's not. There is no memory effect. It's still a completely Markovian process. It's really extracting informations. It's of course through the learning it has learned over a long trajectory, but it extracts all the information that it requires from a single state. So from the forecast state, it doesn't need the previous forecast states. I mean that's something that you can actually do. But here I'm just focusing on the forecast states, and it extracts whatever it needs actually about the uncertainty. It learns a lot of things about the uncertainty only from features in this one single state, this is what is actually so amazing. It's there's no memory. It's a Markovian process.
Okay, thank you very much. We do have more questions, but I think in the interest of time, we should probably move on. So, Marc, if you could kindly write your answers on the OPAD. Thank you.
Yeah. Thank you, James.
And thank you for your talk. Thank you.